Um, okay. So let me start with the last lectures, lecture 6 of the Entanglement Bootstrap. I really appreciate the opportunity to have those long lectures, 6 of them, and each of them with roughly 2 hours. I never use such detailed lectures. This helped me to reflect what were the essential part of the program. And I learned a lot during from the questions and preparing the talks. Let's see what we have for the last lecture. This one is for the mentioning some open problems. Of course, there are actually so many open problems. Each time we do a project, it turns out what we solve are something we find exciting. But in the discussion, you will find a lot of open problems, which is true in the sense that we do find more open problems than we solve during the project. I cannot mention all of them, but I want to touch several of the most important aspects. So I picked a selection of open problems to discuss. But let's first review what we have done. So um, usually we have a Hamiltonian. If we are solving a quantum many-body system as condensed matter physics or mathematical physicists interested in such models, it's usually hard to go from microscopic, the smallest length scale. Right? I guess I should say length scale. So from the smallest length scale of the local Hamiltonian terms, from there to the largest length scale where we expect topological quantum field theory or conformal field theory or the mathematical backbone of the thing could be a unitary modular tensor category and some quantities tells you about the invertible part in 2 plus 1D should be the chiral central charge that people conjecture. But we are the entanglement bootstrap is more like this part to go from the middle length scale. Suppose we have some wave function already satisfy some nice conditions, we can interpret them as a fixed point conditions. We were lucky that we got the right, well, guess the right one. The right to be included. You can argue whether this is the right ones or not, but we made a lot of progress. We have reasons to think those are good ones, A0 and A1, and make a lot of progress. This part, so go from the middle to the large, is what we call entanglement bootstrap most of the time. But now, if this part is successful, then this going from the small length scale to the fixed point will be more and more physically important as well. And there are a lot of important open problems concerning that. Okay, if you have an approximate fixed point, can you show you have the axiom? Or if you have some microscopic Hamiltonian, I guess it's hard to solve everything, but if you have a large class of a microscopic Hamiltonian, can you argue from there that after coarse graining, you should have those axioms? This will be much more valuable than before because previously it's unclear whether the area law has consequences, but now we show there are a lot of important consequences. Now we should go back to the problem, like how the two-dimensional area law emerges. Can you prove that? That's an unsolved problem. But don't try to prove the naive version of the area law because the axiom A0 and A1 determines a more stronger version, but it roughly said we want to remove the dust and the defect, then we should have this. Right. So, and I'd like to comment on one of my favorite video. It's I think it's 1960s or 70s. It's a long time ago, so it should be outdated. So why should I mention this? Indeed, Feynman gave some lectures in Cornell mostly about particle physics. There are 7 lectures in total, and if you look at the first one, the second one, you say, oh, those are the particle physics in the old days. We don't have to watch it now. But the last lecture, I found it still interesting. It's talking about seeking new law. And in the middle of the lecture, Feynman was saying, yeah, how to make progress. Since then, physics, we get some assumptions and make predictions, and then we compare to experiment. If it's right, maybe it's right. If it's wrong, we throw away the theory, no matter how beautiful it is. And he also said that at that time, well, I guess particle physicists are already interested in the idea of symmetry. He said, if you get stuck, there must be something else. Like if it's from symmetry, people have already know that we can get from symmetry principles. They try this all the times. If you try this, you will not be the first one. You get stuck, so you will get stuck by asking the same question. So maybe you need a new idea the next time. History don't repeat themselves. But this one, actually, when I watched the video, I thought, oh, women almost discovered the entanglement bootstrap because see what we are not imposing any symmetry laws. We are using entanglement laws. But you know, actually, Feynman read some quantum information lecture notes in the 1970s. Yeah, maybe he's one of the early people who could have discovered something in this direction. But no, we are guided by much more physical intuitions from lattice model, from topological quantum field theory. Feynman in the 1970s, we don't have that. Right, so we are kind of lucky, so we got more motivation to think about it. And maybe that's why entanglement bootstrap is developed only, yeah, recently. But gap ones. Right. And another thing Feynman said in the lecture was towards the end of that lecture, which I liked a lot, was if you try to develop a theory, there's a lot of uncertainty. How do I know we get the right idea? He was saying that if you try something, yeah, try some idea, if it it's not obviously wrong, but you explain something in a way that's simpler than what people had before, then you're probably on the right track. I hope showed you a sufficient example that you start from those unfamiliar axioms, but make progress that some physical, so we should pursue this theory further. And on the other note, we should be careful in the sense that this is after all some physical theory. It's hard to prove a theory right, and if there are counter examples, you can disprove the theory. It's better put some effort to think about this direction as well. And we disprove this, right? So if we have a large research program, maybe in the future will involve more and more people. Yeah, indeed, more and more young students seem to get interested in this business. If we are really wrong, it's better disprove ourselves as fast as possible so that we are not wasting much resources, right? So those are the open questions as well. Hope we can come up with some test which, if you get some results, you can immediately disprove the theory. Okay. And okay, I'll get started. It turns out I feel like I prepared more than I wanted to yesterday. So yesterday I thought this would be brief lecture, but I saw a lot of pages on the desktop. Okay, I need to start somewhere. Okay, so let me start by here, there. Yeah, let me start by talking about anions. So anions are objects that can be seen by the modular tensor category. They are objects that can break and fuse with each other. And some of you in the audience are experts on that. And to try to review what the entanglement bootstrap said about those excitations, I would say the idea, the first idea is that a vacuum well is is a strict subset of a local vacuum. In other words, you have this annulus. It may look like a vacuum locally everywhere, but it could detect some topological charges. Although the local pieces are the same everywhere, it can somehow have an interesting convex set. Interesting convex set of locally vacuum-like state. Give you the set of topological charges. And this follows from the axiom. I guess I should remind people about the axioms. C and B as BC. Oh, sorry, as C minus SB A0. That's A0. It's 0. And in realistic setup, we should have errors. Let me talk about the errors next. Well, maybe half an hour or even more. But let me first try to say some words about this this non-trivial observation. Why there could be multiple states, multiple in fact orthogonal states. Your A and your B are orthogonal if A and B are different. Intuitively, this comes from the uncertainty principle that you have topological entanglement gamma to be defined as A, C, and B. I'm follow from level 1, so let me call this gamma. Level 1 is a half of the conditional mutual information for the reference state. Yeah, so the gamma could be intuitively understood as some uncertainty. Uncertainty. So if gamma is non-zero, there's some uncertainty to determine the element. That's why we have some convex set. Yeah. So the volume of the convex set is non-empty because we have some uncertainty. But in fact, in entanglement bootstrap, the logic is somewhat reversed. It's like we first have the reference state, within show the simplex theorem, show that logically that we must have a simplex, and therefore the values of leading term gamma is quantized. And if the volume is non-zero, you must have uncertainty, so gamma is non-zero. Yeah, that's the real logical flow under the framework. Yeah, I'm talking about this entanglement bootstrap setup with the reference state on the board, A0 and A1. And working in 2 dimensions, 2D. And we apply this philosophy to a different topology. Because and with some additional idea, is topological. The emergence of topology come from axiom A1. It allows you to deform everything freely, and therefore you can talk about topological regions. Yeah. So for this and so on. Turns out this one has some fusion space. Yeah, this is almost like a category figure that you have A, B filled into C. There's some fusion space, which is this dimension gives you right. And this information is a quantum, so it could be covariant. So the information convex set, so the total disk could contain some parts that's covariant. Yeah, and this one is classical. You have classical and quantum information. There are, yeah, but the others density matrices are locally the same as with the vacuum. So we're instead of looking at the excitations, we are looking at the complement. From the complement, we learn the particle species, learn about the fusion rules, and so on. And those ideas originally is in two dimension. You may wonder how general they are. It turns out the program is more general than that. So yeah, start from the A0, A1 in 2D. You can try to generalize. There are three-dimensional versions. For example, still two axioms. We can call them A0 and A1 in 3D. Where the two axioms, I guess you can easily imagine what's going on. Like by rotating the ball, so the C will be the interior, and B will be the second boundary. That's the three-dimensional version of A0. And you can have the rotation of the even partition of the ball. So the interior is C, the second boundary is partitioned into B and D in this topology. Yeah, and the claim is that you only need the same number of axioms. You don't have more axioms in higher dimension. And if you take those two axioms, the intuition is similar. You have set of locally indistinguishable states. It tells you what topological expectation can have, and you can extract some subleading term, kind of generalization of subleading term, which actually tells you the uncertainty, the volume of the information convex set, or more precisely, that measures the entropy difference between the maximal entropy state in the set and the minimal entropy state in the set, the vacuum state. Yeah. There's an analog of gamma, analog of particle taps and fusion spaces. But of course, in 3D, if you are familiar with the models of 3D topological order, you know there are point particles. Point particles, the claim is that they are detected by the information convex set of a sphere shell. Information convex set of the sphere shell. And the intuitive reason is that particle is inside. Well, particle, if you have particle, the string must passes through the sphere shell. Yeah. But again, in entanglement bootstrap, the logic is a flip. So we first define the information convex set from the extreme point, then we show the existence of string operator. Point particles, flux loops. Well, you use a solid torus to detect it. The questions? No. Right. The point particles are non-local, cannot be created locally, but you can show that they can be created by line operator. And the flux loops are loops that can be created alone by a membrane operator on a disk. Yeah. Yeah, those are familiar objects. We can show they must have the same number, the number of loops equals to the number of point particles, and so on. Yeah. Good. Yeah, that's a good point, and we discussed that. And just to make sure, are you talking about this group? And inspected, but you say it cannot be detected. So are you pointing out some maybe entanglement bootstrap within this framework? Are you suggesting it's impossible to detect the string, or just trying to say that we need to do some more work within the framework? You are suggesting that we need to do more work within the framework, and then we can somehow understand the checker string. Right? Good. And I guess one idea you joined and I talked about.
Yeah. I mean, if you are familiar with 3+1D Tory code, there is not only the trivial string and the M string,
Yeah.
which I think most people are familiar with. There is also the so-called Cheshire string. And if you compute the information convex set in 3+1D on a solid torus, you'll find this information convex set cannot distinguish between the trivial string and the Cheshire string.
Yeah.
And from the categorical viewpoint, these two strings have exactly the same breeding statistics, so they cannot be distinguished from far away. That is, remote detectability in 3+1D is more subtle than in 2+1D.
Yeah. So yeah, and do you agree that Cheshire string is a sort of a condensation of a charge to particle?
In 3+1D Tory code, we have a condensable algebra 1 plus E, and E is the point particle. And if we condense this condensable algebra, we will obtain the Cheshire string. And I think this can be seen in concrete models that E particles condense on the Cheshire string.
Good. By the way, how to spell Cheshire?
CHESHIRE, I believe.
SHIRE. Okay, Cheshire string. Okay. Yeah, good. So let me briefly rephrase. So, Yizhou was saying that there's something called checker string, which is needed for some deep reason in the category theory. Is it called condensation confusion or something? Oh, okay. Yeah. So it's like the idea is that from category inside, people find that there must be something called checker string, and it's well, it should be determined given the category data, and it's related to the point excitation, the point particle E in the 3D Tory code by a fancy way of condensing or something of the string. Yeah, good. Mm-hmm. And
I was also about to comment that so the treasure string would still be considered a point particle. As in his framework, isn't that they can detect point particles also using, so if the condensation completion, if I condense point particles into along one dimension, then I think in his words, it is not detected, just still treated as a point particle.
interesting.
I think it is because E is detected. As in E is detected. But a lot of E, so a lot of E showing up along a line you can talk about that even in 2+1 dimension, right? I can also talk about creating lots of particles along a line. I don't have to talk about that in 3+1 geometry. Exactly.
I know it's not code.
This is why it works.
Yeah. I know that
in
it's violated.
theory, the line is still a particular object, but then if this object is also connected with some one morphism condensation, and that would break A0 and A1, I think.
This one actually break the A1 in some direction. Yeah, A1 is violated in some direction, but some not other. So the intuition is that if you have some information, then there's no problem to translate transport the information along the line, but it's hard to pull something out of the string. The A1 is violated in some direction, but it turns out A0 is good. I checked this on some models, but the puzzle here would be given this setup like this reference state on 3D on a clean, everywhere the axioms are satisfied. Can you come up with something that violates the axiom in a natural way? Okay. Can you create this state with the treasure string from the input? Yeah. Yeah, great. I'm glad that we add some question to the list from the discussion.
Maybe I also have a question. Since of the two categories, they look so, the Casher string looks so similar. Is there an alternative model where it looks like fundamental applications rather than a condensation of dots? No, I mean the actual model. Because right now, let's say creating it using the Tori code, then it is constructed as a defect that I especially need to condense there. But is there a model where it looks more like, maybe look more like a fundamental excitation like the M string, and in that case, compute?
Okay, so his question is that the radial fusion category of Tori code, 3+1 in Tori code is actually the bulk tensor product of two rep Z2. Like there are two rep Z2 and then you do the tensor product. So I think yes, there are pretty lot equivalent to exchange trivial string and checker string. Like map 1 to 1C, like trivial string to checker string and M string to that M string fused with the checker string.
Okay.
So yeah, there is.
Right. So I hope everyone is benefiting from the discussion. Let me just summarize that this is a open question that yeah, we want to answer in some way. It's like there's a way to treat this as an external defect. If I have a state content that for I can say a lot of things, but the relation to particle, how to understand how to use point like particle to condense into that one. Yeah, as you commented, I also agree that in entanglement bootstrap there could be some further progress to understand that aspect. But let me also mention some other ideas related to this uh, this philosophy of local vacuum when we check particle types and fusion spaces. For a single knotted excitation is more complicated in a knotted loop. If you put this on a sphere, you could have some degeneracy, and you can use the complement. Talk about not complement. You can try to understand what's going on, like how, what the fusion space and the properties should have. But the partial this is a partially answered so far. And another thing is that if you have two flux loops and put them side by side and use part of the boundary field. In this way, you get some graph state. You may wonder whether the excitation here should be classified as particles or something peri-fusion spaces. In entanglement bootstrap, the answer we predict that in this shape, if you have a single this shape on a sphere, it don't have an interesting degeneracy. You only have one full degeneracy, and so therefore you should label this by some particles.
Thank you. Maybe the natural way to view one-dimensional excitations in 3+1D models is to view the strings as fundamental excitations. And when we are talking about loops, actually you are specifying how two strings are put together. So they form a certain morphism in the two categories. Yeah, so here we are actually talking about some non-trivial way of gluing two morphisms or pasting, I think this is the more precise term.
Yeah, guys, I talked to you and you can and the answer would be that there should be some way to discuss it. Right?
Yeah, but this is not quite the most fundamental object in the category.
Okay, but it's a fundamental in entanglement bootstrap. That's another interesting comment I want to make. So in the spirit, we could say that, oh, we try to recover some topological quantum field theory. You may wonder whether we are doing this step by step. Whenever we go like one little step, we have something to compare in the category side. It doesn't seem the case. It seems to believe the ordering. Some things that are, as you said, is not the most fundamental in category theory. It turns out to be the first thing we can talk about in entanglement bootstrap. And why that's the case? That's one big mystery. Yeah, right. Part of the mystery. I think is worth spending more effort in the future. So why something that are not fundamental in our spec will be super simple. That even the first step in the entanglement bootstrap, and in a few minutes I will even post some questions. I don't think anyone knows the category analog. So why can we post that question so easily in entanglement bootstrap? Not in the right order, but maybe in the end we get the same thing without going from the same path. We are doing some with different path.
Yeah, I want to make a comment about my answer to Idril's question just now. Like the trivial string is a tensor unit in the Brady fusion 2 category. So if you really want a Brady autoequivalence that maps 1 to 1C, that's impossible because it always preserves tensor unit. So it's not like that similar to E and M exchange in the case. Yeah.
Thank you. I think basically the fusion rules of the Cheshire string and the trivial string are different. For example, if you fuse the Cheshire string with itself, you get 2 copies of the trivial string. Yeah, so I think they are fundamentally different. I agree.
All right. So in response to the more interesting puzzle in 3D, I have to go back and introduce the third idea I have talked about. The idea 3. It's immersion is a valuable concept, and we only need a bomb. Immerse the region. So it's like some local immersion means local embedding. And just to give some reminder to the example we know, is like if we try to immerse the annulus into the 2-dimensional ball, we have multiple choices. One is this, another is the figure 8. And thanks to the fact that we can complete a sphere from the ball, those two are the only 2 choices we need to worry about in 2D. But in 3D, the classes of immersed regions are fancier, and so is the deformation. So the idea is that we have immersed region and we can deform them smoothly. Can deform immersed region to another immersed region. And in 3D, there is a non-trivial example which has a very nice YouTube video of turning a sphere inside out. So if you have a 2 sphere, you can immerse this in the background of 3D in R3. But the puzzle is to turn a sphere inside out without creating sharp corners. You can find this on a video called Outside In. And given that, well, let me try to draw this. So it's like a sphere. Imagine this as a 2 colors, the 2 surfaces, and then what you try to do is to make the red the other surface, yeah, out and this one, the blue one inside. It turns out that this is possible, and if we think about this as a second sphere, that's a sphere shell. The sphere shell, as I said, is detect the point particle. Yeah, detect point particle, and then when we do this deformation, what we do in entanglement bootstrap is that there is a sequence of quantum channels on local regions, local channels, and the region deforms step by step. After a finite number of steps, the sphere shell is turned inside out, which generates isomorphism of the information convex set. So we have this map, phi, and phi would generate an automorphism of information convex set of the sphere shell. Then the puzzle here is to show the following, which I don't know how to show. Puzzle phi of the vacuum state. Is it the vacuum state? And yeah, if the answer is yes, then we will be able to show that. Yeah, if the answer is yes, then phi of rho a would be rho a bar. So the sphere inversion will take particles to antiparticle if this is true. Yeah, so this looks stronger than that, but yeah, it is not so hard to show that they are equivalent. So I want to say, oh, this is a fundamental part that we don't know how to show, but I guess one difficulty is that the immersive region, the immersion process cannot be easily translated into category language. At least I don't know how to do that. And there are many more such problems. You can do some fancy deformation of the immersive region and ask what called as the this non-trivial map acting on the information convex set. You don't have a general tool to translate those answers, those process to category, the diagrams in category, so you don't have a general answers. Why is this case the case? Should we give up or should we develop some more intuition on this? So that's a big chunk of questions. Okay, now I'm going to go back into 2 dimensions. Okay, in 2D, there are some puzzles related to figure 8 annulus. Yes, as I draw here, and I explained briefly that if you want to immerse an annulus into the disk background, there are only two different choices up to equivalence. And the figure 8 is the non-trivial choice, and in particular, the figure 8 cannot be deformed smoothly to the embedded annulus. So the ordinary isomorphism theorem, the powerful isomorphism theorem, says if you deform the region step by step, like adding local bumps and removing local bumps, if you can deform one region to another, their information convex set will be the same. Everything will be the same. You don't need to worry about the positions of the region and so on. But if they are the same, we need to worry a lot. And there's one big conjecture here was that there's some stronger sense of isomorphism. Conjecture strong isomorphism says that if the information convex sets are isomorphic as long as those two regions are suppose we need to suppose the two regions are immersed in a topologically non-interesting region, n-dimensional sphere. In this 2-dimension will be 2-dimensional sphere. As long as they are homeomorphic, then we have the same information convex set. Homeomorphic. Thank you. The image sorry, not the image, the source. This one. So both of the pre-image will be the annulus homeomorphic, and still, no matter how you immerse, even though there are different classes, the information convex set will be isomorphic. This is you can ask a version of about this in different dimensions. Even in 2D, I don't know how to show it. Okay, I know the solution for the okay. So the very special case itself in 2D abelian theory. By abelian theory, I simply mean that for the information convex set of the ordinary embedded annulus, all the extreme points have the same entropy. So the quantum dimension will be 1 for all of them. Then this is true. Otherwise, this is a conjecture. I have mentioned this conjecture before, but I want to add to it a little bit. I want to, give me a chance to mention the hidden assumption in the information convex set. So usually we assume the Hilbert space. We'll assume so far would be this tensor product, meaning that the total Hilbert space is a tensor of a Hilbert space on each side. But this implicitly says that we are interested in bosonic theory. But suppose we are interested in fermionic. How should we do? So fermionic, we should replace fermionic. We should replace this tensor product with a Z2 graded Hilbert space. So let me say this is a fermionic version. The total Hilbert space will be fermionic version of the tensor product. And it turns out this figure 8 does make some make a non-trivial implication on those theory. What do I mean? I mean the following. So take an example of P2 P plus FP superconductor, which is a chiral state with no anions. But the chiral central charge is a half. So right. So the edge is ungappable, and people can create an isolated Majorana excitation on the background if you modify some Hamiltonian term. So the physics would be that you have this thing, you can transfer Majorana by hand by really change the Hamiltonian on the line, and with an endpoint you can transfer Majorana. But suppose we only have a single wave function. What can we do? With the reference state, axiom A0 and A1, actually they have to hold approximately because the state is chiral with finite dimensional Hilbert space. But suppose we have this, then the question is, can we tell anything interesting about the phase by looking at the figure 8? And it turns out one good idea for doing this is to consider the dimension reduction of the annulus. The annulus is an interval times a circle. If we shrink the circle to a point, we collapse the circle to a point, then this will be dimension reduced to an interval, right? On the interval, and each point corresponds to a circle, concentric circle. Only like Cartesians give you a spin chain, a finite spin chain. But the same thing applies to the immersive figure 8. Then you get a spin chain wave function by dimension reduction on the figure 8. Given that the two cannot be deforming each other, you may wonder like what the with the 1D phase. There is a 1D fermionic phase from the annulus. This embedded annulus, another is from the inverse figure 8 to this. You can ask whether they are in the same phase or not. This is the psi 1, psi 0, and psi 1. So you can ask whether question would be psi 0 equivalent to psi 1 as a 1D phase, final depth per unity or fermionic phase.
How do you do this projection? I got a bit.
This one? Yeah. So I drew some onion-like partition of the annulus. So partition into the 1, 2, 3,
Okay.
and then this corresponds to 1, 2, 3.
I see.
Yeah.
And there, when some spins are repeated.
Oh, it's okay because there are 2 layers. Yeah.
Then I'll count it twice. I count it as 2 separate spins when I read on 1 dimension.
Yeah, that's right.
Then, okay.
Yeah, so the dimension reduction. So yeah, two different states on one. You can ask whether they are in the same phase or not. We don't have proofs, but I asked this question to a student here in John McGreevy's group. So according to a student, Xiang Yi, numeric. The answer is no. So psi 0 is trivial in the trivial 1D phase, and psi 1 will be Kitev's. Yeah, so they are different. Yeah, so that's a very strong numerical evidence. We still need to understand this theoretically why this is the case. So that's also to theoretically understand why the answer is no is an open question. So the answer should be no. But why?
I'm sorry, I missed the point where you talk about the fermionic Hilbert space.
Yeah.
Is that related to this? It only happens for this fermionic.
Yeah. So for botanic ones, I don't know any ways to say anything interesting if you don't have symmetry. If you have symmetry, that's a good question. I don't know. Maybe there's a similar open problem for system with symmetries, but for botanic system without any symmetry, I believe they should be the same. So I talk about strong isomorphism. That's about the information convex set. But more generally, I believe there's no way to tell the difference. So everything should be the same. You whether you work with the operator algebra, information convex set, or any other tools, you shouldn't tell an absolute difference which one is the bigger.
Okay, you're saying that if I project it to 1D, then I don't have any physical operator that can distinguish these two situations. Therefore they must be related by a finite depth local unifier.
Right. And the justification of that is that for botanic system without any symmetry, the classification of 1D depth phase would be trivial. That's a unique choice. But for fermionic, we have the chance to have 2 different results. That's why we have a lot to ask this question. And it's interesting that the answer is not the same. Yeah, for P plus FP. Okay. Now to try to to tell you more of the open problem, I need to have some other ideas. So I said the idea of a local vacuum will not imply global vacuum is one idea, and topological deformation is the second idea, and inverse region is the third one. But if I want to talk about a chiral response, like the chiral central charge, I need some more idea. So let me delete some ideas. Okay, I delete this one. Let me call this a modular flow. And entropy response. Right. So the next idea is about modular flow. So given a single wave function, we are allowed to do some evolution of it by its own reduced density matrix. So when I say IAD acting on the state, well, because I didn't really write the definition. So what I mean is we have a rho a b to some power I of x acting on psi. Yeah, so this one should be defined as this, and we call it psi of s. And rho is the reduced density matrix of psi. Psi reduced to AB. Okay, so after this evolution, we can try to understand the entropy response. The entropy response at time equal to 0 turns out to be the modular commutator, which is defined like I log your AB. The expectation value on the same state. Right. But more generally, we can have a sequence of modular flow. That's a general idea. Yeah, I'm going to write down some results, and then we'll see what we don't know. There's a lot of things we don't know in this direction. So first, there is a formula for chiral central charge. So what is the chiral central charge? If you have a gap state at temperature, at finite temperature, and T that's much smaller than the energy gap in the box. then there is some non-trivial energy current near the boundary. So the energy current has a boundary, and let's call it R. So I is pi over tau chiral central charge times temperature square. This could be treated as a physical definition of chiral central charge with some coefficient that tells you the energy current that to the left is more than that to the right. The more theoretical understanding would be if you treat the boundary as a CFT. If we believe CFT description of the edge, then the chiral central charge will be C left minus C right. But then it's a non-trivial problem to try to team up with the understanding of this number from the bulk. So suppose we take a piece of bulk wave function, and we compute this quantity. There are of course earlier ideas, in particular the work by Li and Haodang, like take the symmetric take a log. You see the spectrum are not flat, and they are tell you some chirality and low lying spectrum seems to suggest some sort of CFT. But it's hard to extract those numbers precisely, and it's desirable to have a formula which tells you about the number directly. And we have such a formula for disk partition. Let's pick the disk from the bulk, partition this into A, B, and C. Then we compute the modular commutator. In other words, it's some entropy response correspond to the flow. Like if you modular flow on AB, it affects the entropy on BC, and depend on the plus sign or minus sign, the direction of your flow, the entropy can either go up or goes down linearly. So this thing turns out, we propose this work. That we should have pi over 3 times chiral central charge. Yeah. I would say that this work gives a physical argument, which is by no means mathematically rigorous for many reasons. One of the reasons I will explain physical argument. The physical argument nonetheless correctly predicted the coefficient pi over 3. And there's a numerical test. Right. But there's a lot of things we don't understand. But the physical progress would be now finally we can define chiral central charge from a wave function. So can be treated as a definition. As a definition. The definition of C minus from the bulk. Why is it important to have a definition? Because this is not the first thing that had a definition on the wave function. And we have the topological entanglement entropy gamma that can be computed from this partition. And there's a formula relating to anions. Is a gamma equal to log D, and D is a total quantum dimension. It's like if we have this type of formula, we can define the categorical data, the data of anion theory, in terms of something you compute from the state. And the modular commutator will be a formula to define the other piece of important data, the chiral central charge from a wave function. But now, suppose we believe this formula, we think, oh, this is nice, we want to understand it's better, then what will be the EA square. Thank you. Yeah. We this EA and central charge. Yeah. So suppose we take this as a physical observation and ask whether there's anything deep behind this. Then the next question we would ask is, can we understand the quantization? Is C minus what? Yeah, computed from the wave function quantized. Well, we already answered this analogous question for gamma. The gamma is quantized in a fusion rules from entanglement. From yeah, so we want to ask a similar questions for the modular commutator, but it turns out we haven't been able to answer this, so that's an open problem. Good. What do I mean? So what I mean is the following. Right. So yeah, let me be more detailed. So first, let me draw a figure, a diagram with the gamma and yeah. We know the right question to ask is, can you find a reference state, a state satisfied other area law axioms, or if you wish, the gap ground state, the ground state of gap Hamiltonian large enough length scale, what value of gamma and j can we get? Obviously, we can have this point. At this point, you just take the product state. You will get gamma equal to 0, j equal to 0. And you also know that you can get take the toric codes here. And there are some chiral 7. And E8. More generally, if you take a topological order predicted by the category theory, you should be able to compute the chiral central charge mod 8 and the total quantum dimension. So you can find some points on this plane correspond to that phase of matter. But from the Bootstrap point of view, we want to not only come up with models, we also want to say that some other things you imagine could never be exist. For example, between the trivial state and the EH state, we can ask whether there's anything here or in this window or something, right? In fact, yeah, we already excluded some small value of gamma, so we know that this cannot be exist. There's nothing here. But then how about on this horizontal line, gamma equal to 0 line, can we come up with some unknown base of matter actually give you a different chiral central charge than what category theory predicts? Can we find that such a state, or can we exclude them? And in the entanglement bootstrap, we want to exclude that. Yeah, so the last question would be, can we exclude? And remember that we should keep an eye on disproving this framework and maybe disproving the category predictions as well. Then it will be a nice problem. The search for state with the axioms A0 and A1 hold approximately, but with modular commutator take the strange value, gamma equal to 0 and j equal to some value there. That will be a big discovery. Everyone wants to read your paper. Yeah. Okay, so I think you laugh because you don't believe that the state. Okay. Yeah. Okay. Right. So for modular flow, yeah, we don't know the answer as I said. Yeah, this question is open. But this is a very attractive open problem, so we want to make some progress. And in fact, there are some partial discovery pointing to something, but we don't know if that's strong enough. A, B, and C. Yeah, let me write down one formula that has been recognized. A, B, minus I. Acting on psi is proportional to psi. Yeah, actually, let me let me rewrite. I think I do that better if I make it smaller. Okay, this is the S T S and T the minus. Okay, like I came up with a sequence. We suppose we came up with a sequence of modular flow. It's actually inspired by this combination. So if you see a modular commutator or a commutator, you suppose we learn Lie group. You know that Lie group and Lie algebra has some relation. If you say Lie algebra is some infinitesimal operation of sequence of a group element, then you get some infinitesimal element, right? So this is that flavor. So you have evolution by time t and s. So s and t are real numbers. So you from real, and you do this sequence. So it's designed such that if the operations commute with each other, if I suppose I can move this to the other side of this one, then everything cancels. But because they don't commute, they left with something. It turns out you get some interesting vector. Sorry, actually I rotate down. I rotate in the wrong way. So it should be e to the I s and t times pi over 3. Yeah, it has something to do with s and t. Yeah, it's like that. This formula is stronger than the modular commutator formula because if we take the s and t small s and t, we recover KAB ABC of psi. Well, it's not proportional to psi at all by numeric, but we need some more terms. Yeah, so it's like that. The first line a vector, and plus the second one more like a connecting correcting terms, and give you that where kappa something vertical line something is saying we evolve the state by AB. Well, let's take this. So this one is defined to be D K. for the state. Yeah, so you evolve the state by density matrix on AB, and then you look at how the modular Hamiltonian changes under the parameter to the first order. So the derivative of a modular Hamiltonian. It turns out that appears in the equation. I don't know whether this will be helpful in deriving the quantization of the chiral central charge, but that's something extra we may play with. But I should say this formula is argued based on some assumption is not rigorously established under the axiom. Argued. And tested. Tested on some interacting system, like some analytical wave function of a chiral semion. But this is not proved. Not proved. And recall that the same situation applies to the modular commutator. The modular commutator formula is not proved under the axiom yet. One reason it shouldn't be possible is that there is a no-go theorem. No-go theorem says that on finite dimensional Hilbert space, finite local Hilbert space dimension, we can, so here is non-zero, then A1 cannot be exact. A1 can be exact. Yeah, so yeah, that's why we need to rely on physical intuition a bit more on chiral state. Yeah.
So basically, for fixed point states that satisfy A0 and A1 exactly, we could expect some very good behavior on finite size. Yeah, but for chiral states, I doubt that the finite size statements could ever be proved. Basically, I think if we need a rigorous proof, we need to consider some process of taking the limits to infinite size.
Yeah, great. Yeah, I like this comment. And yeah, in fact, yeah, let me also make a related remark. So I said we should look for opportunity to disprove some beliefs. Actually, this is somehow on this direction, right? So it's saying that when we started this program, we were making the simplest possible case because we have observable models. Then we say, A0, A1 seems to work. We have finite dimensional Hilbert space. We start to prove things on that, and that's tough. And this no-go theorem said, and we somehow get the modular commutator with, and it tells us about the chiral central charge. We are very happy about it, but no, we can disprove ourselves within the framework. We say some of our combination of the assumptions are too naive. If we have all of them, it actually doesn't tell you about the chiral state, so we need to relax them, and that forces us to talk about the non-fixed point, which is physically important. So it actually forces us to talk about this part. Yeah. So even this theory somehow knows about it. Can I say that? Well, maybe I shouldn't say that way because the modular commutator is not haven't been part of it's not rigorously a piece of entanglement bootstrap anyway. But now we are in this situation, we have to talk about approximate axioms. So at year 5, approximate fixed point. The approximation. Yeah. So under approximate fixed point, we have more idea, but less rigorous proofs. And let me mention a few ideas based on that. One is the reconstructed Hamiltonian. Oh, sorry, parent Hamiltonian. Suppose we have a state, entanglement bootstrap state, a reference state on a ball or on a sphere, if you wish. Sphere because you can add a counter. Oh, sorry, you can collapse the boundary to a single point. You have a sphere, but you can also construct a more fancier manifold based on immersed regions, completion, and so on. But yeah, on some manifold, let's see. The state is on a manifold. The psi on some manifold is A0 and A1. So I want to talk about approximation, but let me say one thing about exact axiom. Under exact axiom, it turns out we can have a commutative projector Hamiltonian. These projectors are on the support of some region. So the region AI give you some projector I, defined to be projector on the support of AI. And we arrange AI and AJ in such a way that it's not like that. Yeah, we don't like this because the overlapping is harder to deal with. And in particular, there are 4 regions near a point. We don't want that. But we can somehow do a perturbation near the 2 points to split the region. It's more like this, the ABC. And we have Markov state. IECB is 0. And you have PAB turns out it commutes with the projector on BC. And this commutation projector Hamiltonian turns out to satisfy all the nice properties like topological quantum order, TQO conditions, and the ground subspace gives the characteristic. The correct state means the states in the information convex set are the only state of the ground state. But for approximate axioms, this projector is harder to find the analog because even for very tiny eigenvalues, the projector will, doesn't distinguish the large or small. That doesn't seem promising. However, it turns out for the approximate case, there is another natural reconstructed Hamiltonian. Hamiltonian is sum of delta of B, C, and D, where C is the center of some region. Let's see. C, D, and D. Let's see. Yeah. So this is a region that you have A1 or approximate A1. A1 is true approximately. Then we know that delta BCD will be small. Delta BCD is a linear combination of entropy that appeared in axiom A1. But the delta hat, so what appears in the Hamiltonian term, is the delta hat, which is the operator version of delta. So this delta hat has a property that, well, delta is greater or equal to 0 by strong selectivity. The delta hat is also greater or equal to 0, meaning it is an operator that is positive semi-definite by some operator version of strong selectivity proved by David Lin and collaborators. So this Hamiltonian is non-negative when the ground state almost give you 0 eigenvalue. Therefore, we can physically argue that the original ground state is the ground state, and hopefully show this is a gap. But then there are a set of open questions related to showing what the nice properties. The question will be the open question. Try to understand the justify this is a nice Hamiltonian. It's not simple because delta is the sum of logs, and the logarithm of a density matrix is hard to play with. There are some large eigenvalues to blow up potentially. So it may not be a sum of a bounded Hamiltonian. Maybe there are clever ways to regularize it, make it a delta behave in some way. I don't know which is the best way, but that sounds like a non-trivial mathematical physics puzzle. So to justify this is a nice Hamiltonian. But in the spirit of try to disprove some idea, we can also try to numerically find some Hamiltonian which has some state where the reconstructed Hamiltonian is not a good one. Maybe it has many ground states. Maybe I don't know. Maybe it is a Hamiltonian of a different phase of matter. You start from the ground state correspond to one phase of matter. Maybe you end up with a Hamiltonian that belongs give you a different phase of matter. That happens. Maybe not, but we don't know rigorously whether we always have the nice Hamiltonian. And I've got to rephrase this constraint, this open question to a nice, maybe nicer ones. Is try to prove under entanglement bootstrap A0 and A1 with the approximation. Whether we can show that 2 pi divided by A minus equal to the sum of quantities related to topological scheme and to the quantum dimension. Whether we can prove this formula, under these versions of a entanglement bootstrap setup. And more about approximate fixed point. Actually, we could do something in this direction, and some of my collaborator and I work on separate projects related to this one. For instance, we can ask whether the Hilbert space theorem. So if you are on a torus, for instance, whether this is still approximately fully coherent space if you have approximate A0 and A1. This is a problem I worked with the ETA team during my 3 months in Davis, after I moved, we sometimes when fill in some detail, but I get faded from time to time. We haven't read it, so it adds up. And there are some other ideas from, I think, Daniel. And Isaac. About A0 projector convolutional, which is different from the other one in the exact setup. The idea is that A0 is related to some variation of neutral information. The pure state is more well controlled, and if you have exact axiom, you have exact projector and frustration-free homonomial. And under approximation, they have approximate frustration-free homonomial might be more under control. But yeah, those are some ideas. And in fact, there are some other ideas about vector version, vector approximate A0 and A1. So it's like A1 is a statement that the entropy condition delta BCD is 0. It's a scalar equation. So how about the acting on the reference state is a small vector. And in particular, that means delta square minus delta x square is small. Yeah, so exact A1 implies exact vector version of A1, vector version of A1. But under approximation, if this is some number delta, this number will be some other small number epsilon, which is a function of delta. But the function, like how the scalar version controls the vector version, is not completely understood. But one thing we know about the vector version of A1 is that the modular commutator to be deformed freely under error if we have a vector version of A1 with error epsilon, then we know that the deformation of the region of modular commutator won't give you too much error. So the vector version seems to be useful. And there is a more ambitious conjecture related to the fixed point, so related to RG, the error of A0 and A1. 0, A1 is a approximation. Suppose the errors will be delta 0 and delta 1. So there is a conjecture based on the following intuition. We know that we can violate A1. A1 is not true for every gap state. But if we try to break A1, what we usually find is some finite amount of violation. If you have a non-abelian atom somewhere, you get the violation to be log 2. So it's easy to find delta 1 greater or equal to log 2. A lot of examples. A lot of examples from anions, like a single anion in somewhere, and you take the annulus that centered the disk centered at the excitation, you find greater or equal to log 2, a big violation. And if you want to consider models with a spurious contribution, you get violations of A1. These conditions at a large length scale turns out for all the models I looked at, they are all greater or equal to log 2. So maybe there is a threshold. So that's the idea of having a threshold. And that's a question mark. And based on this, we can write down classes of conjectures. One of the simplest is the following.
Miss, you said delta 1 is always delta 1 greater than log 2, then
happens in a lot of examples.
in a lot of models.
Yeah.
Where it would flow to
this want to flow to a smaller value. Yeah. Yeah, but the threshold is that the idea that if the violation of A1 is smaller than some value, some threshold, it will always decay. So one conjecture you can write down is conjecture if delta 0 decays at exponential minus then divided by the prediction and delta 1 of some length scale delta r is less or equal to some threshold star star. Then delta 1 0 and decays faster than something. Yeah. So suppose the delta 0, the error of A0 decays in a controlled way, and we show that the error of A1 must be decaying if it is smaller than something. Yeah, we know from the data point that the delta star cannot be too large, so it must be smaller than log 2 for this to be correct. Otherwise, we have a counterexample. Yeah, for threshold less than log 2, we don't have a counterexample. I think this is another. This conjecture looks so hard. I don't know how to make progress in the next few years. But on the other hand, I suppose you want to disprove the theory. maybe we can try to find some state that have disproved the conjecture. If we can disprove the conjecture, that means those fixed point, the axioms are not really robust. We better not to use them. But I really don't see such examples. And recently, in terms of make partial progress to test this conjecture, we after I moved to UIUC, University of Illinois at Urbana-Champaign. Yeah, me and my collaborators, John Li and Taijian Yang, we were doing some numerics to test the similar flavored conjectures on mixed state topological order with the volume law. There are volume law version of axioms and violation. The advantage is that on such system we can test on much larger length scale. And apparently the axioms seem to be robust if you have some errors. After we zoom out, the error also seem to decay. But still we are missing some proofs. But there are evidence, but we try to disprove every time we try. We see this kind of RG behavior. Maybe that's a good sign. All right, so I think maybe 10 more minutes to talk about the last conjecture. I think the last conjecture would be very much complementary to the first idea. Idea 1 with the local vacuum give you something beautifully different, but that idea is not enough. Talk about invertible states. Invertible states in arbitrary dimensions. The invertible states are by definition, they are not connected to the trivial state. So if you have an invertible state, and this is the trivial product state, you cannot have a transparent wall. Something interesting must happen. So let's call this as a alpha. This is a, let's say, partial alpha means the boundary. The example would be alpha equal to inconceivable. So the 2 plus 1d E8. The E8 is the invertible state. Well, invertible state is something that cannot be converted to the trivial state either in space or time by a finite depth. If you're familiar with finite depth local unitary idea, the alpha is not equal to 1. This is the time picture. This is the space picture. So if you have E8 partial alpha, the boundary will be gapless. CL minus CR will be 8. If you have a conformal boundary, you can say this. But otherwise, the more general statement is that the boundary must remain gapless. In 3 plus 1D, I think there's something called Walker 1. Walker 1 model has input category being suppose the input category is modular set of categories and bulk has no interesting particles. And the boundary, this time you can gap it out and be gapped. But in all known examples, the boundary will have a non-trivial topological excitation, has anion on the surface. And the anions on the surface is different from any anion contents from the StreetNet model to other commuting projector model. Therefore, it's some sort of anomaly because this model is conventional projector. Or maybe that's not the best way to state the anomaly, but the state is that there are something people argue with being able to prove. For example, they ask the people and they seem to tell me that people don't know the statement about the general gap the boundary. So they have models of gap the boundary. They observe that, oh, this model of boundary has anions. But if I ask whether have you considered all kinds of boundaries, what can you say about all the general gap the boundary for that system? The general feeling would be because you have a bulk anomaly, it must manifest to the boundary. But with the precise statement, can you show that some sort of gap the boundary cannot exist? People don't have that. There's no good theorem. And similarly for 4 plus 1D, there are invertible beyond group homology. These two classified invertible states. The boundary would be 3 plus 1D. Topological order has topological order with a interesting loop excitation. But those are what people sort of know that the spirit was that something interesting happens on the boundary. But in the entanglement bootstrap, the desire is desirable to make some sharper statement as follows. So suppose the n-dimensional bulk So the bulk is captured by some reference state property A0 and A1, for example, in the n-dimensional version of this. And boundary, on the boundary, we can have some boundary version of this on a half plane with the boundary, some boundary version of the axiom on the boundary. Yeah, suppose this is the gap. And can we disprove, like either show the inconsistency? Yeah, the first one is to show you some inconsistency. For example, in the case of Walker 1, we can try to show that if the bulk is captured by the axiom, the boundary, and suppose they have the axiom, we can show the inconsistency in the case of Walker 1 in 3D will be gamma on the boundary cannot be 0. Yeah, if it's 0, then we cannot have such a boundary consistently joined with the bulk. Yeah, maybe there are such statement. And in the case of 2 plus 1D EH state, that will be J being non-zero is incompatible. It's disagreeing. So J is non-zero implies no consistent gap the boundary at all. And for this one, in fact, we yeah, in fact, we have this. So this is the no. Yeah, if J is 0, we can. So why the boundary cannot have a Markov state? So even a segment of the boundary. So this is the bulk. If the bulk is chiral, so J is non-zero, we can show that on the boundary, even any segment that a few coarse-grained lattice size, if it has a Markov state condition, the boundary version of A0 and A1, it's inconsistent, so we cannot get the boundary out. No, this is the open question. Thank you. Let me write this. Yeah, this is apparently an open question. Yeah, similarly for 4 plus 1D. Yeah, those are open questions. Yeah. Yeah, I ran out of time. I didn't say anything about gap history, but I'll stop here. Gap history. Okay. Yeah. Okay. Let me make a few remarks. First, for gap history, we'd better also have a approximate fixed point because we are serial algebra. At least for 1 plus 1D edges, if we expect the emergence of a non-trivial unitary representation of real serial algebra, the Hilbert space needs to be infinite. So yeah, we need to have approximate axioms on any finite scale. And then about RG, a comment about RG would be there is an outstanding conjecture of the quantity C, which is supposed to be a stationary at a fixed point. But how about non-fixed point? How about RG? Question would be is C defined on near the x axis using this local region, whether this is a RG monotone or or C function, right? There is already an entropic C function by Cassini and Wharton. They use some space-time picture but convert this to some gradient of entropy. But this one is different. Yeah, I don't know whether in some field theory people can test this RG in relativistic field theory, whether this is monotonic or not. Yeah, this is the first comment. The second comment would be going to thermodynamic limit, adding set size, adding. So in gap state, we have the powerful tool of immersed region. So when we immerse a region into another, we have a recycled qubit. We can use the qubit multiple times. In that way, we can make a closed manifold such as torus. Once we have the torus, we can immerse another torus in the previous torus. We can make the Hilbert space dimension, making the diameter in the x and y direction goes to infinity. So we can effectively go to thermodynamic limit. We have unlimited number of spins to use because we can recycle them. But for gapless system, can we really have the analog of recycling the qubit? I believe the answer is yes, with two ideas. So first, we have a ground state of CFT. Second, we use modular flow to like squash something into a smaller cross ratio. Well, squash them, change the distance. But with the distance, that's the cross ratio. We change the cross ratio, like putting more and more qubit in a given cross ratio or something, and then try to glue them. So with a circle with a finite partition, maybe as small as 4 partitions, maybe with some axiom is code, we can use this trick to create more and more sites and go to the thermodynamic limit. I think that's doable, but that haven't been done. So that's another open problem.
Other questions? If there are no other questions, then let's thank Bowen again for having given us so many lectures.